Okay, so next up we've got this assembly here. It is a steel bar and an aluminum bar. Each of them are 1 inch thick, so that's like into the page thick. Um, the steel, that kind of the height, I guess. Well, yeah. So the height's 30 inches high for each of them, and then the kind of width of the steel one's 1/2 inch. The width of the aluminum one is 1 inch. So they're connected with pins at the end with a rigid short link. And basically, when we apply a 80-pound force to the link, we want to figure out what the reactions are. So just looking at this here, so got everything here. I'm defining my coordinate system, so I'm going to be defining it in terms of x as this way, y's up, z's this way. So kind of just looking at look in order to kind of orient ourselves in the same way that the uh, you know the predetermined solutions are. I'm going to kind of turn it on its side. So again, this will be that'll be y here, which would make that x. Wait, no. If y is in that direction, then x is going to be in that direction, and then z in this way. So, anyways, just kind of redrawing the links. So again, they're 1 inch in and out of the page, and then the steel one here is thinner, whereas the aluminum one here is fatter, but they're each the same length. So to find our reactions, again, we need to kind of define a compatibility condition. Oh, sorry, I realized my head was covering the coordinate system diagram when I was drawing it there. So again, y is in this direction, y is in this direction, x will be this direction when we rotate everything. So just to find our reactions, we need to have a suitable compatibility condition. So we are going to go with, because the link between them is rigid, we know that they're going to have the same amount of movement at the ends. So our displacement at C is going to be equal to our displacement at D. The other thing we know is that essentially we can treat it as if there is, as if they're individual beams with forces applied to them, but the forces that we apply to the ends need to have when we add those forces up, it needs to equal 80 pounds. So the load on C, and the load at D is equal to 80 pounds. And then just a few givens. So the Young's modulus of the steel, 29 times 10 to the 6 psi. Young's modulus of the aluminum, that one's 10 times 10 to the 6 psi. So for both of these, the case that we're going to be using is C1 from Pytel. So it's a cantilever beam with a point load at the end. Basically the simplest cantilever beam situation you're going to end up with. So the displacement for that loading situation is going to be equal to P times L cubed divided by 3EI. So again, we're going to have to calculate the I's for these. So again, if we're looking at we're trying to determine the rotation about the z-axis. It's a bending moment about the z-axis that would occur. So that'll be the if we're looking at the cross section for the steel, that'll look like this. It'll be 1 inch. That's 0.5 inches. And again, z-axis will be this way, x-axis will be this way, y-axis will be that way. So the base here is 1 inch. The height is going to be half an inch, and 12 is 12. So calculating our I, 1 inch times 0.5 inches cubed divided by 12 gives us a value of 0.0104 inches to the fourth. And then for the aluminum, similar idea, except of course its cross section is actually a 1 inch by 1 inch cube, or not cube, square. So 1 inch times 1 inch to the third divided by 12, that's 1/12 inches to the fourth. So we can take those values and we can plug them into our deflection formula for the two things in question. So again, we got our deflection for C at C, so that'll be for the steel, the end of the steel. That's equal to the load at the the portion of the force on the length that makes its way to C times the length cubed, so 30 inches cubed, divided by 3 times our EI, so times 29 times 10 to the 6 pounds per inches squared times I, 0.0104 inches to the fourth. So number-wise, that gives us 0.0298, and then PC, and then the units cancel out to be, so we got those two cancel out. These inches squared cancel out 2 of these, and then these ones cancel out all but 1 of the inches on the top. So it's going to be 0.0298 PC inches per pound. So if we have some whatever value for P that we have, that's going to be in pounds, so our deflection is going to be in inches, which is what we expect. And then delta D, so the displacement of this thing here when the force is applied. Again, that's just the force applied to the end of that beam times L cubed divided by 3 times R, 3 times R E, which is times our I, 1/12, not 1/2. I realize I'm pretty sure I didn't screw up the actual calculation. But let me just double check that. Divided by 3 times 10 E6 divided by 12. Yeah, no, I didn't end up doing the calculation. I just I think I just drew that too lightly. So anyways, yeah, so our I value, our E value, and 3. So that gives us 0.0108 PD inches per pound. So again, we know these two displacements need to be equal to one another. That's our compatibility condition. So we can just solve for PC in terms of PD. So, PC is equal, so 0.029 PC inches to the pound is equal to 0.0108 PD inches per pound. Divide that out, and we get PC is equal to 0.3624 PD. And the other part of a compatibility condition is that PC is plus PD is equal to 80 pounds. So PD times 1 plus 0.3624 is equal to 80 pounds. So we're able to solve for PD, that's 58.72 pounds, and then PC ends up being whatever is left, so 21.28 pounds. And so I'm just kind of redrawing our diagrams, our free body diagrams here. So again, we got our force at the end here and our reaction. So we're going to have some sort of reaction in X, and we're going to have a moment reaction for each of them. So an AX and an MA, and then a BX and an MB. So I drew the AX and the BX in this direction because I know that's the direction it's obviously going to be. So we can just go ahead and start solving. So for this bar AC, that's the steel one, the force reaction is going to be equal to 21.28. Again, that's in the direction shown, so the negative X direction. And then the moment can be found just by summing up the moments applied to it. So this moment, the reaction moment, minus, the reaction moment, which again we're denoting as positive, and then the moment caused by this thing, that one is a clockwise rotation, so that's a negative moment, so negative 21.28 pounds times the 30 inches. 30 inches there. So that's equal to 0. Solving for MA, we get 638.4 pound forces inch, or pound force inches, I guess, or 53.2 pound force feet, if we want to do it in pound force feet or pound feet. And then BD, similar. So again, our calculation for the forces in the X direction is bloody simple. It's just going to be equal to 58.72 pounds. So again, in the negative X direction because that's how I drew it. And then our MA again is just going to end. Our MB found by summing the forces at B. That's equal to 0. So MB minus, again, this is a clockwise rotation. So it's going to be that one's going to be positive. Negative. That one's going to be negative. And then of course we just assume that the moment in B is positive until found otherwise, and it ends up being the case. So the magnitude of this moment's negative 38.72 pounds times 30 inches, and we're able to solve for B as being 1,761.6 pound feet inches, or if we want, pound force inches, or 146.8 pound feet. And that's our reaction. And that's all we were asked to solve for. Cheers.